Welcome one and all to our 7th weekly discussion session for the Physics of Nanoscale Devices NPTEL course. My name is Jyotishwaran. I'm a PhD student from the Department of Electronics and Communication Engineering, IIT Roorkee. So, beginning with the topics that we shall discuss today. So, in the previous weeks, that is up until, sorry, this is the correction, this is the 8th weekly discussion session. Last week was the 7th. Apologies for that. So, uh, yeah, so for the first 7 weeks, what we have essentially been doing is we have been studying the properties of the channel, like the nanoscopic channel. So if we have short channels where the length is of the order of nanometers, what kind of effects that can be observed, what kind of behavior it will have, how the conductivity of the channel will change, and so on and so forth. Now we shall look at cases where essentially we are now going to form the complete device. Like we are going to form a transistor, which is the basic building block of most every digital device around. So to do that, now the what we have to do is we'll have to take the initial device model that we considered, that of a two-terminal device, where we assumed one terminal was the drain and the other was the source, and extend it by introducing a third terminal. So that will give us what is called the MOSFET structure. So the MOSFET structure is our introduction to the three-terminal device model. So that will be the very first topic that we shall look at. And after that, we shall briefly spend some time discussing the ideal MOSFET characteristics. Now, this is a topic that is not explicitly covered in the course lectures. However, I'd like to cover it here for added emphasis. So you can expect that no questions regarding the ideal characteristics will usually show up in either your assignments or your examination. And after that, we shall come to what I am calling the non-ideal characteristics, but those are the real characteristics of the MOSFET. And in that, we shall look at two particular effects that become that are representative of this non-ideal behavior. One is drain-induced barrier lowering, and the other is called subthreshold swing. So we shall look at these two in a basic sense and see what implications they have on the device performance. So moving on. Oh yeah, sorry. Yes. So this is something that most of us are familiar with. So why did I write conductance? I'm sorry. I should have written the structure. Yeah. Yes. So the structure of a MOSFET is given by the following figure. So we have an N MOSFET and a P MOSFET. So the N or P tells us about what kind of channel we have. So, and this we shall again deal with in the subsequent weeks of this course. However, we'll people who have studied some basic semiconductor device physics or any other related courses would know that the conduction in a MOSFET from source to drain occurs only after there is an inversion that happens in the channel. So whatever semiconductor material the channel is made of, by applying the appropriate gate voltage, we will achieve what is called inversion. Now the inversion effect we'll be studying it in detail in the following week. So I'm not going too much into it. So there will be an inversion where essentially the nature of the semiconductor material will change. Like if it was p-doped, it will become n-doped. If it was n-doped, it will become p-doped. And after that, we will have conduction. So when we have a p-type silicon substrate on which this MOS device is grown, then Upon inversion, the channel will acquire N-like characteristic, N-doped characteristic. So that becomes an N MOSFET. Vice versa, if we have an N-type substrate, then upon inversion, it will behave like a P-type semiconductor. So that is referred to as a P MOSFET. So this is something we'll have to remember. And here again, we are looking at cases where it is possible to, like the flow of current for these devices and the appropriate voltages where we operate in the so-called active region or the linear region of the device. So these devices usually have an associated threshold voltage. I shall come to that in the next section. And for operating an N MOSFET, we need to have our gate voltage above the threshold voltage. And for operating a P MOSFET, we need to have a gate voltage that is below the threshold voltage. And by convention, the current flows out of the drain terminal and it flows into the drain terminal. This is simply ascribed to the fact that the majority carriers in this case are electrons and the majority charge carriers in this case are holes. So that is the reason why we have this inversion in the direction of current flow. Otherwise, the operation of these two devices are essentially the same. As mentioned before, this is a three-terminal device, and the gate voltage controls the conduction properties, most essentially the conductivity of the channel that connects the drain and the source. So this is the basic structure of a MOSFET. This brings us to our first problem. So the first problem is to draw the band diagram of the following device structures. So when I refer to band diagram here, we are not essentially talking about the EK relation. This is not the dispersion relation. Of course, everybody who has studied a semiconductor device course or any kind of introduction to electronics course will know that a band diagram typically uh, moves along like one position coordinate. So if I have several materials placed in junction with each other, we'll essentially move along this axis and say where the conduction and the valence band lies in the respective materials. And what will happen when these materials are brought together under equilibrium conditions. So yeah, I'll also maybe add that statement here. So this is not just the band diagram, this is the equilibrium band diagram. So that is an important thing to mention here, because if the system is not in equilibrium, then well, any kind of technically speaking, equilibrium, yes, any kind of band structure one can argue is possible. So we are supposed to draw the equilibrium, yes. So we shall look at the equilibrium band diagrams for the following device structures. So first we shall look at a PN junction. Now this is once again something that we are all expected to be familiar with. So let us again start answering this in the order. So for this, now for part A of this question, we have a PN junction. So how we shall go about doing this is first we shall draw the band diagram for the for a P semiconductor. So we have the conduction band and the valence band, and since it is P doped, the quasi Fermi level will be close to the valence band. So I have CB, VB, and the quasi Fermi level is, I mean, essentially considered to be the Fermi level because it donates most of the electrons or holes to the system for conduction. So this is the quasi Fermi level EF. And similarly, we have the N-type device. Now again, all standard assumptions apply here. We assume it is the same material, so it is not like two different semiconductors are used. And we'll just assume that it's the same substrate all across and just the doping changes in these two regions. So in this case, again, like essentially why I'm saying that is this band gap will remain the same across the device. the band gap, the distance I mean the energy gap between the conduction and valence band is not going to change. Okay, and in this case, we are going to have EF closer to the conduction band. So this is, let me call this EF1, let me call this EF2. So this is region 1, this is region 2, and this is region 1 is my P-type material, and region 2 is the N-type material. Let me quickly insert another slide. Now, upon forming the junction, so this is part A being continued. Upon forming the junction at equilibrium, now this we have more or less discussed in our earlier weeks sessions, where we were essentially talking about the drain source channel system. But whatever we considered there is equally valid here. At equilibrium, the Fermi level across the device has to be uniform. So that essentially implies that the probability of finding electrons at any given energy should be the same across the entirety of the device. So that is the equilibrium condition. So what will happen is EF1 will become equal to EF2. So let me just write that at equilibrium EF1 becomes equal to EF2. Because of that, let me start by just drawing the Fermi level first. So now this, and let me say this value is equal to some EF. So now this is the value that is EF. And now on the P side of the device, we will have the conduction band being close to, sorry, I've been using red, right? So conduction band, the valence band will be close. And then what we will have is a oh yeah, just I think, should I? I have to, no, I don't have to. Yeah, so, and over here, like I'm going to give a gap and I'm going to say the conduction band is going to be close on the inside. So now we shall connect. So I'll draw the valence band over here. So this is the kind of junction that will form, and again by symmetry, if I have the conduction band over here up to the same point, then we will have a connection that goes like this. Quite honestly, I'm pleasantly, yeah, I spoke too soon. I'm pleasantly surprised with how this figure turned out. It's actually pretty neat. So now this is the conduction band and this is the valence band. And this is region 1, this is region 2. Now we have a third region in this system which corresponds to the junction. Essentially, when we have a PN junction brought together, we'll form a depletion region in the junction where there are no free charge carriers. So this energy barrier indicates the absence of free charge carriers. So we have an electron rich region over here, we have a hole rich region over here, and in the middle we have a depletion region. So this is the like band structure that we will have for a PN junction. So this is the P side, this is the N side. Again, this need not be all linear. It can also be like, I'm just drawing this as a straight line to give a hint. It can also be like not it can, it will generally be a bent, like curved structure. It is not, the energy is not going to vary linearly as I'm moving in this direction. Assuming that they are linear is a good enough approximation typically. Okay, so now we come to part B of the question, which let me just go back for reference. So now that is a PNP bipolar junction transistor. So now that is an extension of this system. So we have a P region, an N region, followed by another P region. So since I've already drawn the P and N band diagrams, I'm not going to repeat that. So this is a PNP bipolar junction transistor. So this is our collector base emitter system. So in this case, what we are going to have is, now I will just uh, at equilibrium again, the three Fermi levels should all be aligned. So this is going to be EF, and we have P and P. So structure will look something like this. Okay, this is a bit too wide. If I'm talking about a BJT, then the base will be relatively thin. So let us try to be as close to. Yes, so this is going to be for a short while, and then it's going to rise again. And yes. So similarly, we are going to have the conduction band, which will look something like this. Yeah, I will erase this P and N and kind of leave it. So no, I won't leave it. I will write it inside here. So this is the P part, and this is the N region. So now, of course, the conduction band energy has to come to the proper level. So it rises up all the way to this point again. So this is going to be, as pointed out before, this is the P region, this is the N region where the Fermi level is closer to the conduction band rather than the valence band, and we have the, oh sorry, not N, it's the P region again, apologies for that. So this is the P region again. So this is how the band diagram will look for the PNP bipolar junction transistor. Finally, we come to the third case, which is the N-channel MOSFET or an N MOSFET. So C is an N MOSFET. What we have to remember is source slash drain of an N MOSFET are N-doped, and the channel is just 1 second. I seem to have encountered a small error. Just give me 1 second. Yes, so there appears to be a minor technical difficulty. I will be back in just a moment. Yeah, so I'm back. Apologies for the delay. So as I was saying, in an N MOSFET, the source and the drain are N doped, and the channel is actually P doped. So insofar as the band diagram for this structure goes, it will actually be the opposite of what we drew. So we'll again have a, following the same color scheme as before, we shall again have the same Fermi level across the three regions in the device. So this is going to be EF, and then we shall have an endo uh, source and drain. So now, so it's going to look something like this. And this, similarly, the valence band will show a similar variation. And hold on. Yeah, I tried to do the whole thing in one stroke. That always comes with its own problems. So this is the P region, and we come back again to the N region. So usually these two variations will be parallel. So if parallelism and things like that are not being maintained, kindly make, like, understand that those things are implied implicitly. So we session. So we come back to an N-type, to an N-type structure. Again, this is going to be more or less equal. I really hope this thing had like a localized erase feature. Yes, so this is how it is going to be. So this region is going to be uh, N-type, N-type. So this is my source, this is the drain, and this is the channel. And of course, this is a P-doped region. Now you can ask where and how the inversion occurs. So for this, I will just take you back to this figure. So in an N MOSFET, we are told that Vg should be greater than Vt. So essentially what happens is we will start applying a positive voltage with respect to the substrate. Oh, not here, over here. Positive voltage with respect to the substrate. So when we apply a positive voltage with respect to the substrate, what will essentially happen is these bands will start moving in a particular direction. Now, in which direction they are going to move, we will see pretty soon. So, but before going into those details, essentially what will happen is when I apply the gate voltage, this barrier over here is going to move up and down. So depending on how that barrier moves, we will have different conduction properties for the channel. Okay, so that comes to the end of question 1. Now, the second topic that we are going to look at, which is the ideal MOSFET characteristics. So a MOSFET usually operates in two regimes, and those regimes are separated by a threshold gate voltage. Like the threshold voltage that we refer to Vt over here is something that is applied across the gate and the substrate. So this bulk object here is referred to as the substrate. So, and typically the substrate voltage is either matched to the drain voltage or the source voltage, but there are cases where the substrate is also biased at its own independent voltage. So all these cases are possible. So although it does not contribute to the current conduction, there is a fourth terminal in this three terminal device, but that voltage is never tweaked or tuned. So that is usually kept at a fixed value. So threshold voltage is what we call VT, and this is applied to the gate. So VT is applied to gate. So now below the threshold voltage, the MOSFET acts as a switch. Now what is a switch? A switch will not allow any current conduction up to a particular voltage value, and beyond that voltage value, it will start conducting current freely. So an ideal switch's characteristic will actually look not very different compared to a diode actually. So we will have a kind of, so on this axis I have the VDS and here I have IDS. So when VG less than VT, what will essentially happen is, for VG less than VT, what will happen is, up to a certain voltage, we will have no current flowing, and then after that, like completely in the theoretical limit, a switch should be a closed circuit, so it should just rise up. But since we are actually talking about a MOSFET and we are saying that there are devices, there are materials here and there, like we have an N-dope material and a P-dope material, we of course know for a fact that that is not going to happen. So what will actually happen is, let me use this color here. What will happen is, up to a voltage, it is going to be nothing, and then it will start rising something like this. Now, at Vg greater than Vt, like when we have the gate voltage which is higher than the threshold voltage, the channel, I shouldn't say channel, oh yeah, MOSFET channels, yes, because I'm referring to all kinds of MOSFETs. So MOSFET channels behave, then I should say behave. That's a grammatical error. Yes. MOSFET channels behave as a resistance of varying resistance. Essentially, as the gate voltage, as the drain source voltage varies, essentially the conduction properties also change. Now, why does that change? Ideally speaking, we expect it to not change, but it does change. So that will give us a curve. So this is for Vg less than Vt. Now again, this is only for an NMOS. So here I should mention that this is for an NMOSFET. Again, for reference, I shall take you back to this figure over here. So this is an NMOSFET where Vg is greater than Vt for the device to be active. Okay, so now for Vg greater than Vt, what will happen is, the behavior is not going to change like drastically. What will essentially happen is, we will have a, like instead of being a straight line, this will kind of start showing a non-linear increase. So again, some approximate trends, we will see what happens when we have the curve. So if I draw another curve like this, and then a third curve which is in red, which is like this. Again, this is the same graph as this. This is IDS versus VDS. So this is IDS versus VDS. So let me say this is VG1, this is VG2, and then VG3. So what I'm going to tell here, I'm not going to tell the relation between VG1, VG2, VG3, because this is dangerously close to an assignment question. What I will tell you is this: for an N MOSFET, increasing the gate voltage increases the conductivity of the channel. So use that to figure out the relation between VG1, VG2, and VG3. It's very simple, but I don't want to do it explicitly because it is an assignment question. Okay, so it's going to be something like this. And this tells us that whatever the resistance which is given by, essentially the resistances or conductance is given by, like, G for this will be given by dV ds by di ds. So dV by di. For a linear thing, dV by di is a constant, so we will just write it as delta V by delta I. And at a given point, we will even write it as V by I if it is completely linear. In this case, we will write it as delta V by delta I. But over here, we'll have to do it, evaluate the derivative at any given point. And as you can see, the value of the derivative changes depending on where we are on the curve. This is not a linear curve. So this implies that the resistance, and by I mean consequently, the not consequently, like resistance is the inverse of the conductance. The resistance and the conductance varies as the applied voltage is increased or decreased. Okay, so these are the ideal behaviors that we expect from the MOSFET. So now we've been asked to draw the output and the transfer characteristics of an ideal MOSFET. Now the figure that I've drawn here, this is referred to as, let me see if I have another color. Yes, I have green. So this is referred to as the output characteristics. We call this the output characteristics because we are just looking at the voltage applied across the drain source. Like if I'm thinking of it as our 3-terminal device system, like if I, like, this is not an accurate depiction of the MOSFET, but if I look at any 3-terminal system and I have a gate on top of this, so this is G, then VDS versus IDS is the input versus output. So that is referred to as the output characteristics. And the other thing, the transfer characteristics, is essentially given by okay, I have to write it as, no, I can write it as y versus x. So IDS versus VGS. Essentially, how does the output current change when I'm varying this control voltage? Okay, so what we have to notice is this output characteristic is more or less the same below the threshold and above the threshold. What I can say is below the threshold, this will be 0 for a very relatively larger voltage, whereas that is not the case when Vg is greater than Vt. So here again I will mention over here that this is oh no, not more colors. Then this is for Vg greater than Vt. Okay. So now again, ideally what I would expect is for a very low VGS, just 1 second. Did I make a mistake? Oh yes, I made a mistake. I made a very big mistake. So this is not the output characteristic, this is the transfer characteristic. Just give me 1 second. Yeah, apologies once again. The technical issue returned. I hope it won't trouble us anymore. Sorry to say, this is, I was wrong about this. This is supposed to be VGS. Therefore, this will be VDS. Yeah. So, um, yeah. So for VG less than VT, what is going to happen is this thing will not even rise. Yeah. So it is going to be like flat all through. And oh yes, of course. It's not going to be flat all through. It is going to be like this. So IDS will, how do I put this? Yeah, I actually need not have drawn two figures here. I only need to draw one figure here. So I will just say there is going to be a, yes, characteristic voltage Vt here, after which the current will start increasing. For other values of currents, this is going to be, yes, now I will actually draw the ideal curve first, and so sincere apologies for the confusion. I will draw, like what I said is correct, but I drew the wrong graph explaining the stuff. So what essentially happens is when we have our N MOSFET, so I will depict now how the device operates below and above the threshold. So let me say there is a V threshold here. This is the VGS axis. So this is an N MOSFET. So less than the threshold voltage, the device should not be active. Greater than the threshold voltage, the device should be active. When I say the device is active and inactive, what I mean is when I apply a drain source voltage, I should get some current. If I'm getting some current, then the device is active. If I'm not getting any current, the device is inactive or it is off. Okay, so this is IDS. Okay, now here VGS should be understood as V between gate and substrate. So this is not gate and source. So gate and substrate, where the substrate is uh, this, the body of the device essentially. Okay, so coming back, yes. So until I cross VT, I will have no response. After that, we expect to see some kind of response from the device. So we will see some kind of response from the device. Now in the ideal regime, again, I will expect it to shoot up, but it won't happen. So I will say that ideally it will be something that looks linear like this. And for a different value of VDS, I will have a curve of a different slope. And maybe for a third value of VDS, I will have a like line with a different slope. So this is what is ideally happening. Not ideally happening, this is what we expect to happen ideally. So this is VDS1. So here this is drain source voltage. Not to be confused with the, this S here is not to be confused with the substrate. Okay, so this is DS2 and this is VDS3. So you can kind of guess because I mean higher the voltage applied across two terminals, we'll expect the current to be also higher. So based on that, you can guess the relation between VDS1, VDS2, and VDS3. However, in a real device, something else happens. So ideally, I will expect there to be a unique threshold voltage that will define or determine if my device is off or on. So it is off until this point, and over here it is on. It is active. So it is off over here and it is active over here. And this is called the transfer characteristics. Yes. Yeah, I jumped a few steps ahead. So this is called the transfer characteristic. So as I mentioned before, this part you will not see in the slides. I'm just telling what we expect in an ideal device. Again, in an ideal device, I will want all these lines to be kind of like um, being like essentially shooting up infinitely, being parallel to the y-axis. But that, of course, is never going to happen because no realistic device can conduct infinite current. So, since that is not happening, we would at least expect some kind of a linear trend where the current is increasing at a certain rate after our device gets active. So, IDS versus VGS. Now this has already been done in the previous slide. So this is referred to previous slide because now we are thinking about an ideal MOSFET. And this is the reason this wasn't covered in the class because what I'm calling ideal is technically also not ideal. But I want to get across the spirit of how this device is operating. Okay. And so this is the transfer characteristic. Okay. Now, yeah. What about the output characteristic? The output characteristic, as I mentioned before, is IDS versus VDS. So it is the like voltage applied across the drain source terminals and the current flowing across the same terminals. Here we are essentially applying the voltage actually in the direction perpendicular to the flow of the current, which is why we call this the transfer characteristic. Because in equivalent models, you will notice that this relationship gives us what is called the transconductance of the MOSFET. And that is where we essentially get the name transistor from. So it is a device that not exposes, what am I saying? That is capable of having both a transconductance and a resistance. So that is where we get the word transistor from. This is mentioned in the lectures, probably in the earlier lectures. So now IDS versus VDS, how do we expect this to be? Now we know when the device is off, no matter what VDS I apply, I'm not going to get any current. So ideally speaking, if I have this axis going like this, if this is VDS, and if this is IDS, then below a certain value of VGS, nothing is going to happen. So just for the sake of formality, let me draw that. And like no matter how many different values of green is not so visible, let me switch to yes, but it's nice, or violet or whatever color that is, it's slightly more visible. So I'm shading it all the way down here. So this color that we see at the bottom of the axis, so this essentially corresponds to the below threshold region. Okay, yeah, let me just redraw the axis once again so that there isn't any confusion. Oops. This is slightly better. What I will do is I will make the thickness a bit higher. Yes. Now this should make things, yes. So this thick line that I'm drawing over here, this corresponds to, let me just now make this as thin as I can. So this corresponds to below threshold or sub threshold. Okay, so this is the below threshold region. Yeah. Now, yes. Now, what happens when VDS is varied? What happens to IDS as VDS is varied? So we want to find that out. No, no alternate colors here. I just want to use this. So what we will expect is, of course, as we are increasing the voltage, we will want the current to increase. And like since I'm saying it's a resistance, we would expect it to be ohmic. So as we are starting to apply a voltage, it's going to be linear. And after a certain point, like the thing is the current, again, we are talking about semiconductors where the amount of charge carriers is essentially small compared to metals. So we wouldn't expect this device to keep supplying a current to no matter how high voltage we supply. Like current saturation is something that is commonly observed in semiconductors. So because of that, we will expect this current to saturate at a particular value. And likewise, we would again expect the, and we would also ideally expect this saturation to occur at the same voltage. So it reaches this point and it saturates. And let me switch to blue here. Again, it will rise up to this point here and it will saturate. So this voltage is something I would be willing to call the V saturation. So I will call that V sat. And this is at say VGS1, VGS2, and VGS3. Again, I'm not giving the relation between VGS1, VGS2, and VGS3 because there are assignment questions that kind of relate to this. However, I will tell you this, for an NMOSFET, the device becomes more active as VG goes above the threshold voltage. So that is why I said below a threshold over here. So if it becomes more and more active, then we would expect, more and more current to flow through the device. So that should kind of tell you what the values of relative values of VGS1, VGS2, and VGS3 are. Okay, so this is the output characteristic. This is the output characteristic of the device. Yeah. Since I've lost like some 5-10 minutes due to technical difficulties, I didn't. You know what the hell? It's fine. So I will just, color match these things also. This is VGS1, this is VGS2. So this is what ideally, again, if I'm being really ideal, it should rise very sharply and saturate immediately. Like it should have near zero resistance. So it should just rise and saturate at different levels for different VGS. But of course, we know that since we are working with semiconductors, that is not going to be the case. It is going to be ohmic. And this is what I referred to as in the active region, the device is going to be working as a resistance with variable resistance or variable conductance. Like depending on the value of VGS, the resistance in the active region is going to change. And the switching behavior we essentially see from this. So if a VDS has been applied, no current will flow if VGS is kept below the threshold. The moment VGS changes above the threshold, the device will switch off. So like, so I shouldn't say below the threshold here. What should be understood here is switching implies like moving from above to below. So it implies this is happening. Like below VT and above VT. So we have these two things and we are kind of moving back and forth. Okay, so we should understand that this process is taking place. So then our device is a switch. And that is typically what happens. So the gate voltages are the things that are switched to achieve the switching effect. So there is a clock pulse, and that usually goes and feeds into the gate voltage of the transistors. And there is an initial VDD or VDS that will ensure how much current flows through the device when the device is turned on or off, depending on the value of VGS that we reach. Okay, so this is the ideal operation of a MOSFET. Yeah, so now I should have, yes, I should have written non-ideal here also. So now we are coming to the final topic of today. Rather than quote the results, which are all present in the slides, what I shall do is I shall go about deriving the, not deriving, kind of like giving a overview of how these characteristics arrive at, because the assignment again for this week contains a large number of theory questions and one numerical question. Our final problem is going to be a hint for solving such numerical questions. So if people have already seen the assignment for week 8, you will know that the order in which I'm covering the topics is more or less the same as the order in which the assignment questions are present. Okay, so now we have to describe the non-ideal characteristics of a MOSFET that result from the material properties of the terminals, the gates, source and drain terminals. So that is A, and we also need to find an equation for the output characteristics of a real MOSFET. So these are the two things that we shall do. So let me insert a new slide. So part A. Now what happens? So what happens is this. When we are looking at the band diagram. So let me just go to the band diagram right now, and right now I'm only drawing the conduction band. Okay. So band diagram. Or band diagram of conduction band. So it is going to look for an N channel as we saw over here. It's going to look like this. That's essentially what I'm going to reproduce here. It's going to be like this, and then it's going to follow. Now what we will see is as VG increases, now like if I have a PN junction, if a positive voltage is applied to the P side and the negative voltage is applied to the N side, then this energy barrier will become smaller and smaller and smaller. So as V increases, as V goes up, this barrier will become small in a PN junction. Now what we should observe is this is an N MOSFET, and I have a P material here and an N material here, and the voltage applied on the P part of the device is going up. So as it goes up, we can automatically visualize that this barrier, so VGS, if it increases, like this is what is happening, then what we will, I will use double arrows to show that transition. So what we will have is, or rather I will use a different color. So what will happen is this barrier height is going to come down. And this kind of makes sense because as I am increasing the VGS, current flow is increasing. If current flow is increasing, then the barrier that is presented to my electron while moving from source to drain should also come down. So this we can tell intuitively. Like if the barrier is smaller, then more electrons will make it over the barrier. Okay. So that is the reasoning here. So as we are increasing VGS, this barrier will come down. If we decrease VGS for an N MOSFET, okay, so again that should be remembered here. This is an N MOSFET. For a P MOSFET, the opposite will happen. Okay, so if VGS goes up, this thing will come down. Again, we have the source and the drain. Okay, so again, these things should be aligned. I apologize for the misalignment, but please understand that these things are aligned. So if VGS goes up, this barrier will come down. And that is essentially where we get the notion of inversion also. Like if I go back to this figure over here, when a voltage is applied, this band will come closer and closer and closer to this Fermi level, which implies after a certain voltage, this band will come so close to the Fermi level that it will essentially behave like an N-type material, which is what we have here. So that is effectively the inversion that we are achieving here. Okay. So remember that these are both conduction bands. This is not the band gap represented here. Okay. So this is what is happening. Now, because of this, we should also know one more thing, that if the barrier height is changing, then let us say I'm increasing VDS. Now the point is VDS essentially tells us how much energy, what electric field I'm applying in this direction, how much force is applied on my electrons in this direction. So for a given barrier height, if I'm varying VDS, then I cannot be guaranteed. In fact, I can tell that this non-zero values of current will start occurring at different values of voltage. So threshold voltage is no longer going to be a fixed value. So that is the first non-ideal effect that we encounter. So how will that become apparent? So that will become apparent like, I mean not apparent, how is that represented? That will be represented by this kind of a curve. So we will have nearly zero IDS and then it will start rising. And of course, since I'm showing that this is current flowing across a junction, you know that such a semiconductor junction never has a linear resistance. So now I can say that it's going to look like some kind of an exponential curve. So let me say that there is, some knee point or something which I can assign to denote the rise in the current. What will happen is at a different value of VDS, again, I'm not going to say if it is higher or lower, at a different value of VDS, it might take a slightly higher VGS for me to achieve the same current. So if I'm looking at the variation of VGS and IDS, then this will kind of happen for VDS1 and VDS2. Now I'm explicitly telling you what physical process is taking place here, so that should kind of give you an idea as to which of these VDS is higher. So because VGS gives me the characteristic of this barrier height. So as VGS increases, the barrier height keeps coming down. Even if the barrier height keeps coming down, the increase in current is relatively slow here, which implies the electrons that are approaching the barrier don't have that much energy in them. So that should tell you about what kind of voltage is applied across the drain source junction. I've almost stated the answer here, but I'm not going to explicitly state the answer for the assignment questions. Okay, so this is how the non-ideal, again for the sake of completion, if I were to say go back to photograph, yeah, we can also have a third curve that rises even sooner, and I will say this is VDS, and let me call this VDS 0. So I have VDS 0, VDS 1, VDS 2, and all of them will have different, the threshold voltage is no longer a unique point, which implies now the device can actually turn on and turn off not at a fixed value, but at a slightly not fuzzy, like slightly broadened range of voltages, which implies the switching behavior is no longer accurate. So what we will actually need is to distinguish this. We will need to find out a case where, like, we will need to find out a gate voltage where the change in the current, like the increase in the current, is so high between the off state and the on state that I can clearly distinguish them. So now that quantity is given by this derivative. It is given by, now I want the current to change. I don't want it to change by a factor of 2 or factor of 3. I want it to change by orders of magnitude. Okay, so if I want the current to change by orders of magnitude, then what I shall do is I shall take the derivative of log to the base 10, not 2, 10 of IDS by dVGS. We shall essentially look at this quantity. Now this tells us, now log will effectively tell us the power of 10 that is closest to IDS. So how many powers of 10 is changing when I slightly shift VGS? So that will tell us which of these three curves I need to choose. So yeah. So that will give us, yes, this value, and this is the quantity that is referred to as SS, or the sub-threshold swing. Essentially, this tells us sub-threshold swing. This tells us how much the current increases, jumps by or swings by as I'm moving across the threshold voltage. So this is usually measured at Vt. This quantity is measured at Vt. Okay. So that value of VDS, like that value of, I mean, I shouldn't say this is measured at Vt. The point at which this value goes above a certain threshold is what we fix as Vt. Because now we can no longer look at this kind of a model and say, okay, there exists a single Vt. Now, since this whole behavior is very dynamic, I will have to find a point somewhere over here where the rate of increase really kicks up, identify that point, and then choose that as the like threshold voltage for the system. So that quantity is called the subthreshold swing, and so I mean, essentially, this is, we don't take this quantity, like we take the inverse of this. So we take the inverse of this quantity, this whole quantity. So now this needs to be as large as possible, which means that the inverse of this should be as large as possible. So that implies I need to change the voltage by a very large amount to get the switching action done. So if I have a current curve like this where even slightly switching the gate voltage brings me a very large change in the current, then even fluctuations can trigger my switch. I don't want that. I want a case where only a very large change in the voltage actually activates the switch. Not very large, like relatively large. So that is why we take the reciprocal of this quantity, and we want this to be as large as possible. So typically we want SS to be greater than or equal to 60 millivolt per decade. So this log of IDS is usually taken with respect to some standard value of the current. So this is always IDS by some I naught. So this is 60 millivolt per decade. And decade is increased by a factor of 10. So every time IDS increases by a factor of 10, in order to increase it by a factor of 10, we would need to apply 60 millivolts. Like the voltage change should be 60 millivolts or more. Then we are willing to accept that as a properly functioning switch. Okay, so this is essentially, this is first part of question A. Okay, now, so this is the first non-ideal behavior which we are studying as subthreshold swing. Now, we are still in part A. We are going to part 2. Now, part 2, rather than looking at the gate voltage, now we are going to look at the VDS or VSD or whatever, like the drain source voltage. So now I have the source. Again, we are only looking at the conduction band. Again, the reason we are looking at the conduction band is because we are looking at an NMOS device where majority carriers are electrons. Okay, so we have the barrier that is formed because of the gate voltage. Now we are not worrying about the gate voltage. The gate voltage is staying more or less fixed. Not more or less, the gate voltage is fixed. It is not varying. Now, given that the gate voltage is not varying, this is D. So when VDS is equal to 0, I would expect these two to be at the same level, and therefore the band will look like this. I really hope this thing has, wish this thing came with a, like, local eraser that we have on things like MS Paint. But somehow it's just getting rid of the whole stroke. So this is at VDS equal to 0. Now what happens, let me assume that I am applying a positive voltage at the drain. Now again, if I am applying a positive voltage here, that implies the drain will start going, like the conduction band will again start going down, like it will move down. Because the energy change is Q times V, and Q, the charge of the electron, is negative. So increasing VDS will actually bring this down on the energy scale. Okay. So as VDS is increased, what will happen is, so we'll have the barrier go up like this, and now the symmetry will no longer be maintained. So it will look something like, it will start falling right away. Oops. Yeah, I've dragged it too far off. Oh god. Okay, this is getting annoying. Yeah, so it's going to be something. Yes, it's going to be something like this. So here I'm going to extend this line all the way over here. And I'm going to say this is VDS. And so this is the case for VDS greater than 0. Okay, so now why is this happening? Like, why am I deforming my, so this is S and this is D. So this happens precisely because now these two are no longer at the same voltage. And because of that, what we have is this barrier, which I expect to be held constant. Like here, I expect this barrier to be held constant. But because of the, sorry, just 1 second. Yeah, so because of, why am I not? Yes, because of the non-zero drain voltage, this barrier is also kind of getting dragged down, because see, for much of the channel length, the barrier is, I mean, it won't be, actually, yes, it can even be this low. So it will keep getting dragged down constantly. Now, since that happens, what is actually happening is now the electron actually doesn't require as much energy to travel from source to drain. It will actually travel much quicker, which implies, again, if I would like to have to use this device as a switch, the gain in current will increase But I don't want that, because to have a good switch behavior, as I mentioned before, I want to apply a sizable voltage, like something greater than 60 millivolts to gain a factor of 10 improvement in the current. So if I'm somewhere in the microamperes, to move from microamperes to hundreds of milliamperes, I expect to apply at least 60 millivolts more to the gate terminal. Now, if this barrier is getting lowered because of the drain voltage, then maybe when I apply less than 60 millivolts, I will still get the 10 times current increase that I expect to see in the switching behavior. So that also takes us away from our ideal switch, the not the ideal, like the properly functioning realistic switch that we wish to have. So this phenomenon is called drain induced barrier, oh not D, yes, barrier lowering, abbreviated as DIBL. And this effect, as you can guess, will become more and more profound the longer the channel is. Now for that, I will just quickly go back to our band diagrams here. Like essentially this width of the depletion region, or the width of the region where this sloping, like essentially the bands are kind of bending, this depends strongly on the length of, like, the size of the samples. If the samples are very small, then this much bending actually cannot occur, because there aren't enough electrons in the materials, electrons and holes in the respective materials, to create a depletion region that is that big. So if my channel is very long, then DIPL will become more and more profound, which is why nanoscale devices are a preferred, at least in principle, they are preferable. Because if we have a short channel, then effects like DIBL can be mitigated to a certain extent. It is not that DIBL will never occur, but the impact of DIBL will be significantly reduced. Okay, so DIBL increases with channel length. So these are the two non-ideal effects. And so, like, combining both of them together, what will essentially happen is, if I have a source and drain, then the band diagram will look something like this. It will look, yeah, just, it will look something like, raise it, it will fall to a lower value. For a lower value of gate voltage, of course, the barrier height will be longer, or barrier height will be higher, I shouldn't say longer, and it will kind of maintain its value for a longer point, and it will fall again to come down to VD, and so on and so forth. Like for even lower gate voltages, it will just barely rise and it will immediately start falling, which implies at this point it more or less conducts freely. Like there is a very meager barrier in this case. So this is the direction of increasing VG, and what is to be remembered is uh, oh no, I can't have that. So really, okay, yeah. So I'm just going to draw the line here. So this is the drain, this is the source, And as VD increases, this line will keep moving further and further down. So this is again increasing VDS. This will go down. So the barrier height will go down if VGS is increased. The barrier lowering occurring due to DIBL will also increase if VDS is increased. So to avoid that, either we have to work in the very low voltage regime, which is not advisable because then the system becomes susceptible to noise. So it is better to operate at slightly higher voltages, not too high though, because then we'll be dissipating a lot of power. So this is the combined effect. Effect of SS and DIBL. So I can also like draw maybe curves of a different color going to a different height of uh, uh, VDS, but I hope this is enough to understand. Okay, so these are the non-ideal behaviors. This brings us to part B. Part B of this question, we are required to obtain an equation for the output characteristics of a real MOSFET. This derivation has been done in class. It's there in the lectures. So essentially, if we just look at the channel, then there is a current flowing from left to right. I shall call this ILR. And there is a current flowing from right to left, which I shall call IRL. So IDS, so this is my source, this is my drain. IDS, I drain to source, which is the convention that I'm taking, is IRL minus ILR. Now the thing is, there is a PN junction here, there is a PN junction here. Now we know across a PN junction, I is proportional to e to the power minus whatever energy gap is here. So let us say the barrier that is present over here, barrier height. So I shall call that so delta E divided by KBT. So this is like this essentially comes from derivations that we do in the case of like PN junctions to get the Schottky equation and so on and so forth. So we expect this to be proportional to this. So in other words, I will say I is equal to some saturation current IS e to the power minus delta E by KBT. Now I will assume that it's the same substrate through and through, so IS will be more or less same. So it only depends on the barrier height difference between the channel and the drain and channel and the source. So there are two barrier heights that I need to look at. That is why I'm writing this derivation at this page. So the barrier height will be between this and this for the left-right current, and the barrier height will be between this and this point for the right-left current. Okay, so for any applied voltage. And this kind of graph takes into account both like the presence of the gate voltage as well. Okay, so we know this to be true. All right. So what we can do is we can simply write. So now let me move to the next slide. So I can write ILR left to right to be IS times e to the power. Did I write minus here? Oh no, it is e to the power plus. I'm sorry. Yeah, because as the oh no, it is minus. It is minus because the charge is negative. Yes, higher the barrier, lesser the probability of the electrons crossing that barrier. Okay, so it's as simple as that. So this is IS times minus E channel and source. So I'm going to call this ESC divided by KBT. A slightly different notation would have been used by Professor Vishwet. IRL is going to be IS into e to the power minus ECD or DC. I'll just write it as EDC. So divided by KVT. Okay, so this is the current flowing from right to left. So from this, I can say IR minus IRL minus ILR, which is IDS. So this quantity is IDS according to our definition. This is equal to IRL into 1 minus. So we'll essentially get e to the power, like q is a negative value. So here like q, okay, I will need to write this here. Q is equal to 1.609 into 10 to the power minus 19 coulomb. So this is technically the charge of a proton. This is not the charge of an electron. So E will be minus of this quantity into applied voltage. So minus of minus will give me plus Q VDS divided by KBT. Okay, so this is for I, like this is like what I've essentially done is I've written this as IRL into 1 minus ILR by IRL. So ILR is given by this. So if I like LR by RL, I will divide by this. So IS and IS will cancel each other out. I will get ESC minus EDS. That is essentially the energy difference between the drain and the source itself, which I can write it as Q times VDS. So this is equal to IDS. Additionally, we also have this expression. IDS can be written as the width of the channel into Q at x equal to 0. So what do I mean by x equal to 0? I've drawn this figure here, right? So the channel, so this is the channel. Let me use a different color here. So this is the channel in the middle. And what I'm saying is this point is x equal to 0. And this is x equal to L, where L is the channel length. Okay, so whatever charge I have at x equal to 0 multiplied by, oh sorry, let me just change the color. I need to erase this. Just 1 second. So Q at x equal to 0, which is essentially the charge in the channel, multiplied by Vt. This quantity is the thermal velocity of the electrons. So at a given temperature, what velocity the electrons are traveling with. Okay, so this is the thermal velocity. We shall, like pretty soon, we shall start looking at each of these quantities, like how they can be represented. Now this is usually Q of VDS, VGS. So this we shall study in what is called channel electrostatics, which will be the next topic we shall look at. And this thermal velocity is essentially what we get as the injection velocity. This is also something we shall study in the channel, in the course. And W is the width of the channel. So whatever charge density I have into the width multiplied by this is going to give us the total current. Like we are assuming a 2D channel here. Okay, otherwise this would be the area of cross section. I will also mention that here. We are assuming a 2D channel, which is actually not an inaccurate assumption, because even if we have a bulk device, the inversion layer that forms, like even if we have a device like this, the inversion layer that forms between the source and the drain is a quasi 2D region. So this assumption that the channel is 2D is actually not a bad assumption. It is a very realistic, valid assumption. Okay. So we also have this. Now what we know is the total charge present in the system can essentially, like, the current is achieved by the movement of the charges in this channel. So the difference between the currents will tell me the current moving in one direction. If I just add the currents as they are, then that should kind of give me the average amount of charge that is contained in the channel. Okay, so what I can write is Q at x equal to 0 can be written as ILR plus IRL divided by, oops, divided by W times Vt. Now, what we can say is, we can just take this quantity and substitute it here. So what I'm going to do is, I'm going to write this as, again, I will pull out IRL to be common. So this is IRL into I, not I, control Z, yes, 1 plus ILR by IRL. Now I know this quantity because I've already derived that value here. Divided by, whole divided by, this is W times Vt. Now I can substitute this value into this. So what we will get is, should I use W? Oh, no, I don't have to use W. Here it's only divided by Vt, if I'm right. Let me just quickly check that, just so that I don't make a mistake. Let me just look it up. Nah, it's fine. Okay, so now this is the value of Q. Now what I can do is, I can just substitute this whole thing over here. But before doing that, what I can remember, I mean, what I can see from here is, this implies IDS by IRL is equal to 1 minus exponential QVDS divided by KBT. So this we kind of can get directly from here. So what we will get is, like, essentially we'll substitute the value of Q over here, and then we will divide the whole, like, we'll substitute the value of IDS by IRL, and that will give us finally wait a second, am I correct here, or should I write it as, oh, I'm writing it as e to the power e, right? So this is minus Q times V positive. So, oh yes, the minus sign will not get swallowed. The minus sign will be present here. So the minus sign will also be present here. I'm sorry, I made a small mistake with the sign. Not a small mistake. Yeah. So that will finally give us the expression IDS is W into Q at x equal to 0. We are essentially just back substituting the quantities. Like, this is essentially the magnitude of the charge. This is not the sign of the charge. So this is, I should technically write modulus over here, times thermal velocity into 1 plus e to the power minus QVDS. Oh no, minus the numerator. KBT divided by 1 plus e to the power minus QV, it's not VD, VDS, QVDS by KBT. Yes, so this is what it is. Now, this is essentially of the form, which implies IDS is roughly of the form some constant. So I naught into 1 plus e to the power, sorry, not 1 plus, 1 minus e to the power minus x divided by 1 minus e to the power, sorry, 1 plus e to the power minus x. So this is the function. So to sketch the graph of this function, what we can do is we can just look at the limits where x is equal to 0 and x equal to infinity. And of course, observe some other things. So first and foremost, like in the limit x tending to infinity, both of these quantities will be 0. So I will get ID is equal to I naught. So this I naught is actually the saturation current. So for very large values of VDS, that is when this x will become infinity, I know that my current will become more or less flat. And also at x equal to 0, you'll see that this is 1 minus 1, which is 0. So it starts at 0. Now for very small values of x, I can write e to the power minus x as 1 minus x. So for small x, e to the power minus x is approximately equal to 1 minus x. This is for small x. So immediately after VDS equal to 0, this is 1 minus x divided by 1 minus 1 minus x. So this will be essentially uh, x divided by 2 minus x. So again, for small x, 2 minus x is almost 2. So that is approximately equal to, so this function will essentially be equal to I naught times, which implies IDS will be approximately equal to x divided by 2. So I will have a straight line, and I know that eventually it saturates. So the graph will look something like this. Yeah, I should have. Oops. So the graph will look something like this. So it will be straight for the most part. Then it will kind of start saturating. It will, like, the slope will start becoming smaller and smaller and smaller. Okay. And in the limit v tending to infinity, this will become parallel to the x-axis and will achieve value I naught. So there is, I naught will always be greater than this curve. So whatever saturation current that we are thinking of. So this will kind of rise like this. And this is the, like, real, not, I shouldn't say this is completely real. There are like many more effects that need to be considered. But in our simplistic description of the device, of the MOSFET device, this is the non-ideal output characteristic. So this is the real output characteristic. So it will, the ideal output characteristics that we drew look something like this. Again, this is not going to happen. So we come full circle, and then what we shall have are curves like this. So there will be another curve which will kind of again rise somewhat linearly up to a certain point. Then it will also, like, the hope is at some point these curves will all like become parallel to the x-axis. Okay, because now remember, this q depends on VDS and VGS. So depending on the value of VDS, this q will change. So I naught will keep shifting for different values of VDS. I naught is not a global constant. Okay, so in reality, the output characteristic of a MOSFET will look something like this. So now I can even get rid of the I naught. Now that I have established that it is no longer a constant, it is not a relevant quantity anymore. So I don't even have to consider it. So this will be VDS1. Oh no, VGS1. Sorry, not VDS1. So this will be GS1, and this is going to be VGS2. This one is going to be VGS3. And this is, yeah, let me just extend this axis. PDS, this is IDS. So this is the realistic uh, output characteristic. So this is the non-ideal, or let me just say this is the realistic output characteristic of the MOSFET. So with this, we have more or less covered all the theoretical parts. So now, why have I put a hyphen here? There is no hyphen there. It's just a full stop. That too, it occurs in the bracket. Yeah. So now, the final problem that we shall attempt today is we are considering a MOSFET that is operating at a fixed gate voltage. So we don't have to worry about the variation of the gate voltage. Now, what we are told is that drain source current is measured at VDS equal to 26 millivolts. Now, what we are supposed to find is the factor by which the current will change if the value of VDS is doubled. Okay, VGS is remaining a constant, and as an added thing, what I will say is assume that I naught remains constant, like this I naught constant that I defined here. Assume that when the voltage is doubled, this does not change by much. Okay, so I will also state that here. Assume I naught from previous slide remains constant. So now there is a reason why I've chosen the values that I've chosen. I mean, we should know by now, and we can also assume that this device is operating at T equal to 300 Kelvin. So first thing we have to notice is, so this is the answer, at 300 Kelvin, kBT is equal to approximately 26 millivolts. So that is why I said VDS is 26 millivolts. So if, sorry, milli electron volts. So Q times 26 millivolts will correspond to 26 milli electron volts. Okay. So IDS that we are initially measuring is equal to I naught into 1 plus. So this whole quantity from our previous equation, this thing is kind of going to become 1 because this is 26 milli electron volt, this is 26 milli electron volt. Okay, so this is going to be 1 plus E divided by, oh sorry, it's 1 minus E divided by 1 plus E. Okay, so I don't know why I erased the whole thing. 1 minus E divided by 1 plus E. So now this will be, we can quickly calculate this to find out that, so this will come out to be this as a value of, just 1 second, let me verify this once more. Oops. should be 1 minus e. Yeah. Okay, I made a small mistake, but doesn't matter. We can just, like, the answer will come out to be negative, but don't worry about it. I should have actually chosen a slightly higher voltage. Uh, it's fine, it's fine. So this will come out to be uh, roughly, approximately this will be minus 0.5 times I naught. So yeah, that is why I took some time to recheck the answer. It was turning out to be negative, but that doesn't matter. The idea is to understand the spirit in which the calculation is happening. Now, when this voltage is doubled, what will happen is the exponent here, oh wait, I am wrong. It is e to the power minus 1, not e to the power 1. It will be positive. Yes. So that is where the confusion came from. Let me just recheck the value. Yeah, it shouldn't turn out to be negative, because for any small positive voltage, MOSFET will give us like some current. So that will be, so this is going to be 1 minus. Yeah, so it is going to be not minus 0.5, it is going to be plus 0.5. So my original answer was wrong. So this is approximately 0.5 times I naught. Now, when, again, going back to this formula, when the voltage is doubled, this quantity will become 2, because Q times VDS still will be like twice 26 millielectron volt. This is going to be 26 millielectron volt. So when the voltage is doubled, the new IDS prime, IDS dash, is going to be, I'm told that I naught can be assumed to be constant. So that is going to be 1 minus e to the power minus 2 divided by 1 plus e to the power minus 2. So now that is going to be, so that will come out to be 0.76, but I'm approximately writing it as 0.75 I naught. The idea is to get a feel for how much this changes by. So what is the factor by which it changes? So IDS dash by IDS, that is essentially 3 by 4 divided by 1 by 2, that is 3 by 2, so that is a factor of 1.5 times, which implies it increases by 150%. Oh, sorry, it doesn't, it increases by 50%. Like it becomes 150% of the initial value. So it was 0.5 I naught, it becomes 0.75 I naught, approximately. So this kind of gives us a feel of how much the current increases in the channel when VDS is increased at a fixed VGS. So this is usually how the values will vary. However, you should remember that the value of current, like what current is being mentioned and what voltage is being considered, should be taken into consideration. Like if somebody is saying they are only considering the current flowing from, say, source to the channel, then we are looking at ILR. We are no longer looking at IDS. So in this derivation, you will have to consider the expression for ILR and substitute the appropriate values and find out what is happening. The reason I'm mentioning that is, well, it's an assignment question. I've told you how to do the calculations. You can go ahead and choose the correct formula and solve that particular assignment question. With that, we come to the end of today's discussion. We shall meet again same time next week. Thank you all for listening.